Okay, let's do the exact same example. Here's the memory, there's the cache, but this time we're going to do a four-way set-associative cache. This time a block of memory does not go to a particular line, but it goes to a set. In this case, it would have four choices. In a second, we'll do an 8-way set-associative cache too. That should get us the whole idea. That means there would be 8 lines per set, 8 choices for each block. It's like saying instead of getting a parking spot assigned to you at school that is just yours, you only have one choice. Other students might be directly mapped there too, but you only get one choice. Now there would be 4 parking spots that you're allowed to use. For example, if 3 are full, no problem. You can use the empty one. Up here, if yours is full, there's nothing you can do but have that car towed away, even if you're surrounded by tons of empty parking spots. Over here, you're even more flexible. There are 8 lines of cache in a set, so you would get 8 choices. If one was empty, you could pick that line to go in. And if they were all full, for example, you pick the least recently used, the most stale line, evict that, and you take their spot. That helps us use the principle of locality to make sure you get hits. This time, we have a tag set in Word. You can't tell which line you're going to be in without using an algorithm, so you can't tell ahead of time. So I'm changing that to a set. I'm not going to change this 128 words per line, so it should be clear that the word bits are not going to change. However, you cannot find the tag this way anymore. At least there's another step, so I'm going to get rid of that. For a 4-way set-associative cache, that means you're trying to find out how many sets are there total. Well, there are 2 to the 12 lines of cache divided by 2 to the 2, because I'm going to do a 4-way set-associative cache for now. Forget this one for now. Divided by 2 to the 2 sets, lines per set. If we divide that, the lines will get cancelled out, and we get 2 to the power of 10 sets per cache. Well, take the logarithm of that. There are 10 bits to pick a set. After that, you'd need to find out who got here first, who got here last, who was least recently used. I'm not interested in the line anymore. Just which set do you get mapped to? Well, there are 17 bits out of the 28 used. That leaves 11 here, which is actually what I expected, because before the tag was 2 to the 9. The tag was 9 bits. Now, there are 2 to the power of 2 lines per set. There's that much more competition. Even though you're competing for more lines, there is more competition. So the tag goes up. The sets went down. There are fewer sets. That's the answer for how many bits represent the tag set in Word. The middle 10 bits are the set. You can't tell which line. That's not a relevant question for a 4-way set-associative cache. Finally, let's try a 16-way set-associative cache. Even more. Let's try 32-way set-associative cache. That means there are 2 to the 5 equals 32 lines per set. A block of main memory has 32 choices. You would take the least recently used and evict that. So, the words will not change. I haven't changed this at all. The sets, well, the sets in the tag will change. I haven't changed the main memory either. This hasn't changed. This is the only thing that's changed. 32 lines per set. So now I'm going to change this. 2 to the 12 lines of cache divided into 2 to the 5 lines per set leaves us 2 to the 7 sets per cache. Now there are 7 bits, the logarithm, the exponent. And then there are 14 bits for the tag. We know that this is 2 to the 9 times bigger. Main memory equals 2 to the 9 times cache. And then we can also multiply that by 2 to the 5 lines per set. That will give us the tag. That's the extra step that we need to directly calculate. Those should be 2's. To directly calculate the tag. That's our answer for a set associative cache.